Yeah, good afternoon to all. So yesterday we discussed about the chiral drugs, and we discussed the expected question from that chiral drugs here. And today we will see some important chiral drugs synthesis. Okay, so as we discussed yesterday, so you know that the chiral drugs which are having the right, which are they plays an important role. Chirality plays an important role in the uh, medicinal chemistry. Okay, so due to having the difference in the right, the isomer means the isomers, right? So the due to the difference in the orientation of the groups or the location of that particular atoms or the groups here, so they will differ in their activity. And some drugs are showing the more activity, and some drugs are not having the activity or the less activity here. And where the drugs or the compound, the isomer, which is showing the more activity, generally we call that is a eutomer, and isomer which is showing the less activities are the inactive is called the distomer here. Okay, and eurythmic ratio and the case studies for this particular right due to sorry distomer and eutomer. So all these are we discussed yesterday, and Pfeiffer rules here. Okay, Pfizer rules. So all things we discussed yesterday. And today we are going to see some important synthesis of the paradox here. So in this, first we'll see the synthesis of S-ibuprofen. Okay. So in the chiral drugs, generally for ibuprofen, you can found one chiral center here. So as per that principle, as per that formula, like the number of stereoisomers possible for this compound, like 2 power n, here the n equal to the number of chiral centers. So for this ibuprofen, it is carrying one, what is it? So one chiral center. So the n equal to 1 and 2 power 1, that is called 2 only. So there are two isomers are possible for the two isomers are possible for this ibuprofen. That is R ibuprofen and S ibuprofen. And among these two ibuprofen, where the R ibuprofen is having the less activity, or it is inactive compound generally, right? It won't carry any biological activity or the pharmacological activity. And where the yes, ibuprofen is having the biological activity or the pharmacological activity. Means it is yes, ibuprofen is acting as a drug, and R ibuprofen is it is inactive towards your pharmacological activity. Okay, so we'll see the synthesis of this yes, ibuprofen, because it is a very important and very very good drugs towards the acting as a painkiller here. Okay, so you know that the ibuprofen basically in the normal, right? So normal language, we call it is a brufen. Okay, painkiller here, and it is a non-steroidal anti-inflammatory drug, NSAID. Okay, non-steroidal anti-inflammatory drug here. Okay, and how it is generally synthesized. So here the S-ibuprofen structure is this one here, and you can see that the structure and having one chiral center. And generally, the synthesis of chiral drugs involves two methods here. One is classical synthesis. The classical synthesis where it involves using of the reagents or the chemicals here. Okay, it is synthesis is done by using the reagents here. And one more method to synthesize this compound is the chirality pool synthesis. The chirality pool synthesis involves the using of the chiral reagent here. Okay, chiral reagent means you know that the chiral catalyst. Okay, in the asymmetric synthesis, you are aware of that chirality, right? Chiral catalyst here. Okay, so like binol, binap. Okay, and okay, so like that, the synthesis is done. So in the examination, they will ask any method here. Means they will ask the synthesis of chiral drugs. Means by giving the example. For example, yes, ibuprofen synthesis, write a synthesis of yes, ibuprofen by chiral pool method, or by a right. So or by a classical synthesis here. Okay. So first you read the question and you understand what they are asking here. Okay, which method they are asking. Okay, so you write the appropriate synthesis. For example, if they ask to write the synthesis of chiral pools, right, chiral pool synthesis. So instead of that, if you write that classical synthesis, so you will lose the marks here, right, or vice versa. For example, if they ask to write the synthesis of by classical synthesis, classical methods. So if you write the chiral pool synthesis, so you won't get the marks here. So you see the question and you get understanding of the question, and then you write that corresponding means the suitable answer. Okay, so first we'll see the classical synthesis. And in the exams, if they are not mentioned a particular, then you can write any one. Okay, so sometimes what happens here, so they will ask write the synthesis of ibuprofen. In that case, you write anything. Okay, you can write the classical approach or the that chiral pool approach. So if they are particularly asking, then you write that appropriate one. Yes. So now we'll see the classical synthesis of ibuprofen, and this synthesis involves very simple methods, and it involves very simple reagents, and simple steps are involved here. So we can see where it is they are taking the benzene here. Okay, so where the you see here the benzene upon doing the Friedel-Crop alkylation reaction. Okay, Friedel-Crop alkylation reaction. It, okay, with isobutyl chloride, right? So this isobutyl chloride in the presence of aluminum chloride. So when they underwent the Friedel-Crop alkylation reaction, where this isobutyl group is okay, isobutyl group is gets attached with your benzene, and you know the mechanism of the Friedel-Crop alkylation reaction. Okay, so where this isobutyl group is gets attached with your benzene, right? And we got this isobutyl benzene. Further, upon doing the acetylation reaction, and again it is involves a Friedel-Crop acylation, right? So here is alkylation. This is acylation, not alkylation. Generally, some mistake is there, so you can see that it's not alkylation here. Friedel-Crop acylation reaction. Okay, acylation. So upon Friedel-Crop acylation reaction with acetic anhydride. Okay, so with acetic anhydride, where the acetyl group is going to substitute at a para position of this benzene here. Okay, so at para position where the acetyl substitution is taking place. So generally it is electrophilic substitution reaction. In both cases, Friedel-Crop alkylation reaction and Friedel-Crop acylation reaction, where it involves a right. So it involves a electrophilic substitution reaction, and further this particular right. So acetyl group, okay, acetyl group is undergoing the that nucleophilic substitution, sorry, addition here, right? Nucleophilic addition with hydrogen cyanide, HCN, right? So upon treating with the HCN, where you can see the H plus CN minus here. So this nucleophile is adding at the electrophilic carbonate center here. Then we are getting this cyanohydrin derivative. And this cyanohydrin further undergoing the reduction in the presence of hydrogen iodide and the red phosphorus. And we are getting this, okay, so dehydration. Simply you can say the reduction, okay. So where this cyanohydrin is undergoing the reduction, and we are getting this particular methyl cyanide like derivative here, okay. And further, it is undergoing the hydrolysis, and you know that upon hydrolysis of cyanide group, so where this cyanide group converts into carboxylic acid here, right? So when it is undergoing the hydrolysis here, the cyanide group is converting into carboxylic acid, and we are getting this the isomeric form, racemic form of the ibuprofen. Okay, so we will get the racemate here, plus and minus, the both isomers. Okay, we'll get the both isomers here, R and S. Okay, R isomer as well as the S isomer. So we'll get the racemic form. We call this the racemic mixture here. Okay, racemic mixture. Racemic mixture. What is racemic mixture generally? Where the combination of both isomers like R and S. Okay, so we'll get in the racemic form here. And you can separate this racemic mixture, right? The two separate, you can separate the stereoisomers or the enantiomers, right? By using that, okay, syncoidine base here. Okay, syncoidine base, like we call this process separation of isomer or the separation of enantiomer is called the resolution method. Okay, resolution nothing but the separation of isomers here. Here is a racemic mixture here. So where we are separating the individual isomers, R and S, and we need the S isomer, not R isomer. So we can discard the R isomer and we'll take the S isomer, because this is the useful compound and R isomer is not useful one. It is inactive compound. So you can discard that particular R isomer here, and you can take further, right? So S isomer here. So this
sir,
is
I have doubt, sir.
yes.
Sir, sir, ನಾವು ನಾರ್ಮಲ್ ಬೇಸ್ಗೆ ಈ ಸಿಂಕೋನ್ ಇಚ್ಚಾರ ಸರ್ ಈ ಬೇಸ್ ಡಿಫರೆಂಟ್
నార్మల్ బేస్
ఈ సింకోనిడిన్ బేస్ అని ఇచ్చారు సార్ ఇక్కడ
syncoidine in base. So that is
different
normal base. The base is chosen, that is based on that the compound, right? Here is you see this is somewhat the bulky compound here, right?
sir.
Okay, so where here it is carrying this particular acid group here, right? So it
Sir.
may form that some chelation with this. Okay, so if you use this syncoidine base, right? So it may form some chelation with this one. Then you can see here is the two isomers are there, right? So
Sir.
among these two isomers, this syncoidine base it is attached with one isomer. It won't attach with the two isomers here. If you take the normal base, right? So it will be attached with both, means it will be react with both. So in that case, you cannot separate individual one. That's why we are using the selectively. We are selecting the base. So here this particular syncoidine is, it is very selective base towards that racemic mixture here. So it reacts with or it attach with one isomer, and the other isomer is free from the base. So you can see, right? So you can separate easily. That is the difference of the normal base and this syncoidine base.
Okay, sir. Thank you.
Yes. And the chirality pool synthesis. So this is somewhat your about synthesis only, but only thing is here we'll use the, right? So for the separation here, we can use the chiral catalyst. Okay, you can use the chiral catalyst. Here is we are using the for the resolution purpose. We are using this particular syncoidine base here, but here we are using that particular chiral catalyst. That is a difference. And you know that this chiral catalyst is very highly expensive one, but you will get the more yield. The only application or the only advantage of this using this chiral catalyst is, so we'll get the more yield here. And in the above case, so won't get the yield. Means we get the yield, but we get the less yield here. Okay, so that is the advantage of this chiral synthesis. And this synthesis also same steps are involved here, where the first step involves the Friedel crop alkylation reaction. Then the isobutyl chloride is going to attach with your benzene. Then we are getting isobutyl benzene. And further, we are undergoing the Friedel crop acylation reaction with the acetic anhydride. Again, the electrophilic substitution reaction. We got this particular acetyl substituted isobutyl benzene. And further, we are going to nucleophilic addition reaction with the hydrogen cyanide. Then we get the cyanohydrin, right? And further, where you can see the dehydration reaction is taking place. Okay, so here you can see here the dehydration, right? So in the previous case, some different reaction means we are doing the reduction, right? In the classical approach, we are doing the reduction after addition reaction with the hydrogen cyanide. Okay, we done the reduction here with the hydrogen iodide phosphorus, red phosphorus. But here, where we are doing the hydrolysis here. Okay, so upon hydrolysis, you can see, right? So where this, okay, here the hydrogen. So, and it is going to remove the water molecule. Okay, dehydration reaction is taking place here, right? So dehydration reaction, we are doing the dehydration. So minus H2O is taking place, and we got this particular, okay, what is it? Vinylic isobutyl benzene here. Okay, paravinyl isobutyl benzene. At this stage, so we are using the chiral catalyst. Like we can use a variety of catalyst here. So you can use the binol or binop here. Okay, you can use the binol or binop, or you can use any other what is that Wilkinson catalyst, right? So variety of catalysts are used, means available here. So you can use appropriate catalyst here, right? So here also you need to take care of that, use the appropriate catalyst here. So here they are used the binop here. Okay, binop nothing but here bis-naphthalate. Okay, bis-naphthalate, bis-phosphoryl ruthenium. This is the binop ruthenium catalyst here. You can see the structure here in the below. So this is the, there are bis-naphthalene here. Okay, two naphthalines are bonded here, attached here, and here you see the tetraphenyl phosphane, right? Tetraphenyl phosphane, where it is chelating with your ruthenium metal, right? So we are getting this ibuprofen here, right? So only thing is here to avoid the getting the racemic mixture, right? The advantage of with the chiral catalyst is, so we won't get the racemic mixture here. In the previous case, in the above case, you can see we got the racemic mixture here, plus and minus ibuprofen, right? And you see while you are doing the synthesis, right? Whether it is drug synthesis or any chemical synthesis. So if you get the isomers here, right? If you get the isomers, so it is very difficult to separate the isomers here. Even though in the research also, in the PhD level also. So that's why the researchers or the scientists, maximum they are trying to avoid the chiral compounds generally, means in the research field, especially in the research field, the students, because they don't have the much time here. Okay, and it is very expensive to separate that thing. That's why the researchers are the research students here, PhD students. So maximum they will take up the scheme without chiral centers here. Even I also choose that, means I also take care to avoid that chiral center, because if chiral center is there, so it is very difficult to analyze that one, and it is difficult to separate that isomer, right? So to avoid that, that difficulties, so it is better to choose the scheme which is not having that chiral center. Right? So if you are getting the scientist, if you are getting the scientist job, if you are the scientist here, then you can do the many experiments, right? You can go with any things, because you will get the salary, and you will get the budget for that, and you will get the funds for that to carry out some research and other things here, and you will provided some research laboratory, right? Very encouragement will be there. That's why we can do many experiments on that one, because the funding will be there. Okay. So here also what we are doing here in the classical method, where we are getting the isomers here, right? That racemic mixture. Later we are separating with syncoidine base here. Upon resolution, we are separating this ibuprofen. And here also the difficulty is, so we won't get the 100% pure compound. Sometimes we'll get the some impure compounds also. Again, you have to do the separate that isomer, means racemic mixture. So there is a loss of the product here, right? So it is very difficult to handle with the chiral compounds. Not only the drugs or any normal products is there. If it is carrying any chiral center, so definitely you will get the isomers there, plus and minus, whatever. Right? You will get the R and S, or the plus or minus isomers. So the resolution is very difficult, right? So you cannot separate with column chromatography, right? So in the what is TLC also, you will get the spots very closer, right? So to lift that closer, to increase that closeness, or to decrease the closeness, or to increase the gap between two spots here, you need to use many means highly polar solvents here. For that, you need to make the for the concentrate, right? The concentration, you have to manage that concentration here. So it is very means what I am trying to say is, so it is difficult to handle with this chiral compounds here. Okay, fine. So to avoid this, to avoid the getting the racemic mixture, so we have to use a chiral catalyst, right? So with chiral catalyst, we get only one isomer, the enantiomeric pure compound. You will get the enantiomeric pure compound here. 100% product will be obtained here. But the difficulty is the chiral purchasing of this chiral catalyst is very expensive. The chiral catalyst is very expensive here, right? Whatever the ruthenium catalyst or any what is that rhodium catalyst here, right? Copper catalyst, whatever. So many catalysts are there with some, what is that, metals here, metal catalyst. So it is highly expensive. It's worth nearly the 5 lakhs, 6 lakhs. Sometimes it is 10 lakhs. Catalyst also there. Okay, so 2 lakhs, 3 lakhs, ranging from 1 lakh, 2 lakhs, like that, right? So being a research scholar or being a student, so we cannot bear all these things here. Okay, anyhow, so the procedure is this one. So if you use a chiral catalyst here, so then you will get you can avoid the formation of the racemic mixture, and you will get the enantiomeric pure. Here you can see the yield is 87%. Okay, so you will get the yield of 87% and enantiomeric pure 83% here. So you get, it is very good yield here. Okay, so that is the difference of. Next, the compound is synthesis of naproxen here. Okay, so naproxen here are for every means every drug synthesis, we have two methods here: classical approach and chiral catalyst approach here, or the chiral pool approach. So this is also very means the steps are very simple here. Okay, steps are very simple, but we have so many drug synthesis here. We have nearly 10 to 12 synthesis are there. So it is difficult to remember all the synthesis here. So what you do is just selectively you take some. Okay, selectively you select some drugs like ibuprofen and propranolol or captopril like that. Okay, you take three or four drugs. You select the three or four drugs and you prepare well with all these things here, right? And if you try to memorize or remember all the prepare all the synthesis here, then definitely you will get confusion here. Okay, if you are the extraordinary memory, then you can. It is better to go with this. But my advice is to you select some important like ibuprofen. It is that's right. So repeatedly, it is a repeated question here. And propranolol also it is easy to remember here. And one more drug I can say uh, phenolapril. So this is some difficult here because structure is very difficult. Ramipril also, and you can go with this. Diltiazem is easy. Okay, diltiazem easy, but it is important, right? So sometimes it is repeated question here. Diltiazem also. Okay, ion channel blocker actually diltiazem. Okay, so we have 8 to 9 synthesis are there. So you just you okay, you then 3 or 4 synthesis now. Out of 8 or 9 synthesis, just you learn 3 or 4. Okay, so here this next one is naproxen also important here. Yes, naproxen. So we'll see the classical synthesis. So here where they are taking the beta naphthalene here. Okay, the starting material for this naproxen is naproxen is beta naphthol, and simply they are done the methylation reaction with the DMS OH. Means in the basic condition, they are added the DMS, dimethyl sulfate. Okay, dimethyl sulfide here. So generally the DMS is methylating agent here. So where this substitution of this methyl with the hydrogen takes place in the beta naphthol, and it gives the nerolin. Okay, so what is this methoxy? Okay, methoxy naphthalene or methyl naphthyl ether. This is the very important compound that is we call this is the nerolin. So nerolin is one of the important right chemical, so which removes the nail polish here. Okay, so the girls are they are passionate to apply the nail polish. Okay, and if you don't want to that nail polish, if you want to remove that, right? So no chemical will be removed that one. So if you use this nerolin, okay, so it will be removed. It is nail polish removal here. Nail polish removal, nerolin, and synthesis is very simple. Simply you take the beta naphthalene and you add the DMS, dimethyl sulfide here, and you get the nerolin. And we got this methoxy naphthalene, and further again you go with the Friedel-Crop acylation reaction with the acetic anhydride. Then acetyl group substitution is taking place on this particular naphthalene derivative, and further doing the nucleophilic addition reaction with the hydrogen cyanide. Okay, so we got this particular cyanohydrin, right? Cyanohydrin derivative, and further they are done the dehydration reaction. Okay, upon dehydration reaction. So upon dehydration, where you got this particular unsaturated, okay, cyanide derivative here, and upon hydrolysis reaction, right? Upon hydrolysis, the hydrolysis reaction, where the cyanide is converting into carboxylic acid here. Okay, and this carboxylic acid further means carboxylic acid derivative. So upon doing the reduction, okay, upon doing the reduction with the hydrogen catalyst here, the hydrogen catalyst, you can take any copper catalyst here. Okay, so palladium catalyst here, hydrogen palladium catalyst. Okay. So upon the reduction with the hydrogen catalyst, where this particular the unsaturation becomes saturation here, and we got the racemic mixture of your naphtration here. Racemic mixture of your naphtration, and further we are using the means we are doing that resolution process by using naphtration syncodine, right? So naphtration syncodine, it is one of the base compound here, where it is going to resolve the racemic mixture of your naphtration, and it is separates your naphtration here. Okay, so you see this is somewhat similar steps are involved as your ibuprofen here, right? So in the ibuprofen also same synthesis is done, means same steps are there. Only thing is the starting material is different here. So it is very easy to remember these two, naproxen and ibuprofen. Yes, naproxen and ibuprofen. Okay, so you go with like this comparison here. Okay, so you remember the synthesis with the comparison of these methods here, right? So there also where the Friedel cup acylation reactions takes place, further the addition, nucleophilic addition is takes place, dehydration is takes place, then hydrolysis is takes place here, right? So some steps are common in both cases here. Okay, yes. So we got this fraction here, and the chiral pool synthesis again here very simple. Okay, so in the chiral pool synthesis, actually you come with the from you start with the beta naphthol. Okay, here in the textbook they are given only the right by taking this particular unsaturated what is it? So here some mistake is there, you can see. Right, so here actually here CS3 is given, but this is not CS3, so it is carboxylic acid. So, right, so here it is not CS3, so it is carbox COAH group here. Okay, you make it the correction as it is COAH. Okay, yes, so then here they are done with the chiral hydrogenation, means chiral hydrogenation catalyst here. Okay, so chiral hydrogenation catalyst, you can use the Wilkinson catalyst here, rhodium catalyst. Okay, so by using that you can resolve it, or you can separate that particular directly. You can separate that fraction here. Okay, so by using the chiral hydrogenation catalyst here, so you can separate the fraction. Or or you can use the binop also. Here also you can use the binop here. Okay, as your earlier ibuprofen. Here also we can use binop here. Okay, and you can separate the pure form of your fraction here. Okay, and propranolol. Here is a propranolol. All these are the anti-hypertensive drugs here. Okay, and the derivatives are there. You can see the only some part of the drug is different. Due to that difference, we have the variety of names for this propranolol here. So the core structure is here. Okay, here this is your core structure. Yes. Right. So this is also important and easy to remember here. Only the epoxidation here. Okay. Yes. So here, this is your core structure. Okay. This is your core structure to produce variety of anti-hypertensive drugs. Okay. Propranolol, atenolol. Okay. So here, they will differ in the R group here and AR. Okay. So AR is the aromatic moiety here, and R is some alkyl moiety is given. Due to this difference, we are getting variety of the analogs. Generally, we call the analogs here. Okay, we got the different analogs under this antihypertensive drugs. Then we'll see. And the synthesis of this core structure is very easy. Okay, so where it is done by using the epichlorohydrin here, right? So this is epichlorohydrin. So where this is a epoxide ring. Okay, so where this epoxide ring, where it is attached with the methyl chloride, right? And very simple substitution with uh, phenoxide ion, right? The substitution, very simple substitution done with the phenoxide ion, where the chlorine is substituted with the phenoxide ion, and we are getting this particular epoxide methyl phenoxide here. Okay, then further, the opening of epoxide ring is taking place here, right? The opening of epoxide ring is taking place where this particular epoxide ring opening is taking place with what is it? Yes, right. So here where the nucleophilic substitution here is taking place generally because the RNH2, right? So this particular amine is acting as a nucleophile here. Okay, and yes, you see the lone pair electron in the nitrogen, right? So it is going to attack with where it is attacking here. Yes, yeah. So here you can see in the epoxide ring opening. Okay, in the epoxide ring opening, generally it prefers the sterically less crowded terminal here, right? So here we have the two terminals here. Right, you can see here, for example, this is A, this is B here, right? So two terminals here in the epoxide ring, where this base is here. There are two possibilities, like so it may be attacked here, and it may be attacked here. Okay, so where this attacking of this terminal, okay, this is B, for example, this is A, for example, right? So attacking of base at B terminal, right? So where the OH group is, this OH group is coming on this side here, right? And your NS, this part is coming here, and OH is coming here, OH here, like this. Okay, and attacking of this base at sterically less crowded A terminal here, right? Where this type of opening is takes place, and OH is coming in between that particular group compound here, right? So generally, the base, okay, the epoxide ring opening takes place sterically less crowded terminal, right? Because here you see it is di substituted here, right? The di substitution is there. There is no substitution, okay, unsubstitution. There is an unsubstituted terminal. This is di substituted terminal here. So it prefers to open here. Then this epoxide ring opening takes place like this here. Then we are getting this particular intermediate compound. Okay. Then very simple. Okay. Where you see means attachment of the variety of R group and AR group. So we are getting the different analogs of your antihypertensive drug. So for example, in place of, right? So in place of your R, right? So this is the core molecule synthesis. And here, for example, if you want to synthesize the propranolol, okay, propranolol. So you have in the aromatic right moiety, you have to take the naphthalene here. You can take the naphthalene, and you use the base what is this isopropyl amine. You take the isopropylamine. In the R place, you take the isopropyl group. Then you get this propanolol. Okay. For example, if you want to synthesize the etinolol, okay, if you want to synthesize the etinolol, so you take the base isopropyl amine. Isopropyl amine base is used to open the epoxide ring, and in the aromatic means in place of aromatic group, instead of naphthalene, you have to take the what is this? Yeah, benzamide. Okay, so you use the benzamide here. So it becomes etinolol. For example, if you want to synthesize a metaprolol, right? So as usual, the base should be used the isopropylamine. Okay, so in all cases, you have to use the isopropyl amine. Okay, so in all cases, to synthesize the propanolol, etinolol, and metaprolol, the base used is the isopropyl amine only, but you can use the aromatic moieties. The different aromatic moieties should be used to synthesize variety of analogs here. To produce the propanolol, use the naphthalene ring here. And to synthesize the etinolol, you take the benzamide. And to synthesize the metaprolol, you have to use this particular, what is this? Yeah, methoxy, right? So methoxy ethyl benzene. Okay, so methoxy ethyl benzene should be added. Means you take that particular in the place of AR, right? Means here you see you react with the OAR, right? This is phenoxide ion. No? So in the place of phenoxide ion, you take that particular methoxyethyl benzene. Then you get the metaprolol. So it is very easy to synthesize this propanolol and etinolol and metaprolol here. Only thing is you take the epichlorohydrin here and you treat with the phenoxide ion. Means when the substitution is takes place, where the chlorine is substituted with the phenoxide ion here, then you will get this particular epoxide phenoxide ion here, phenoxide derivative. Then you treat with the variety of bases, okay, isopropyl amine. Then you will get this core structure, core molecule, okay. And by taking the different substituents here, so we'll get the different products, right? So very simple synthesis. And chiral pool synthesis of this antihypertensive drugs like metaprolol, okay, propanolol, and etinolol here. So here the starting material is taken as, what is this one? It is yeah, alpha beta, and this is alpha beta gamma. Yeah, beta gamma unsaturated alcohol here. Okay, so you can use the unsaturated alcohol. Then you can go with this
Sir,
sharpness epoxy.
allyl alcohol అనొచ్చు కదా సార్? సార్ అలైల్ ఆల్కహాల్ అనొచ్చు కదా సార్? అలైల్ ఆల్కహాల్ అనొచ్చు కదా సార్ దాన్ని?
Yes, okay. Are unsaturated, no? Okay, allyl, right, nice. This is
Ah,
allyl alcohol only, not vinyl, allyl. Okay, good. So it is allyl alcohol. Okay, you take the allyl alcohol and you treat with this particular sharpless, means you go with the sharpless epoxidation. You know the sharpless catalyst. Yes, I think somewhere the catalyst structure is given. Yeah, they are not given sharpless structure. Okay, sharpless catalyst structure is not given actually. So you can find in the Google, or you can search in that. It means in our asymmetric synthesis topic, so you can find the structure of sharpless catalyst. Okay, so with TBHP, it is protecting group. Actually, here the TBHP is a protecting group here. So first, what you do, you protect with you protect this particular this particular unsaturated olefinic group with TBHP, right? And you can go with this sharpless epoxidation here. Then we'll get this epoxidation. Okay. Then further you can treat with this, what is this ArSO2Cl, means sulfonyl. Okay, benzene's sulfonyl chloride. Okay, benzene sulfonyl chloride. So where this substitution is taking place, you will get this epoxide benzene sulfonyl chloride derivative. And further, you can treat with the what is this alpha naphthol. Okay, alpha naphtha anion here. Okay, right? Alpha naphthoxide. So you can say alpha naphthoxide ion. Right. So by alpha naphthoxide ion, so you can get this particular ether derivative. Okay, ether derivative here. And further, you can open the ring, epoxide ring with isopropyl amine benzene, sorry, isopropyl amine group here. So here also you can okay, do the opening of epoxide ring from sterically less crowded position. So any compound, right? Any compound prefers any reagent. It may be base or anything here. So any reagent, it prefers the opening of epoxide ring from sterically less crowded position, right? And you remember, if you use right acid, okay, base as well as the acid here. In that case, okay, so the epoxide ring opening takes place from the sterically more crowded position. Okay, because right, so you will get the more stable carbocation is formed here, right? So that is different case here. If you use only right the base alone, then it prefers to open the epoxide ring from sterically less crowded terminals or the center, right? In the presence of acidic medium, okay, in the presence of acidic medium, so it opens, the opening will be takes place from sterically more crowded. Okay, yes, okay, fine. So here this okay, this ether derivative of epoxide ring opening is taking place from sterically less crowded center. Then upon attacking of your isopropyl, yes, so isopropyl amine, right? So where this lone pair electron, this nitrogen, so it is attacking on this terminal, then this opening is takes place like this, right? So then you will get this some, right? So where this OH and what the stereo center is formed here, right? And here generally where the because we are using the chiral pool synthesis, so the one isomer, okay, the one isomer will be react with or one isomer will be lifted by that chiral catalyst, and the enantiomeric pure isomer, that is a S-propanol, will be obtained as a pure form here. Okay, so the advantage of this chiral pool synthesis, only thing is we will get the enantiomeric pure product. That purpose we are using this chiral pool synthesis. And in the classical synthesis, in the conventional synthesis, right? In the conventional synthesis or the classical synthesis, so the disadvantage is where the possibility for getting the racemic mixture, and further it is very difficult to separate the racemic mixture. And so many means there is a loss of product here because for the workup, okay, for the workup here, so we'll lose more compound, right? So we'll get a very less yield. Okay, so that is a difficulty with your classical approach or the conventional synthesis. And the advantage with this chiral synthesis is we can get the more yield and enantiomerically pure product here. Okay, and one more method here, so like ARCO process and chiral pools. So two methods are given. So, but we remember only one method here, right? So we can remember chiral pool synthesis and the classical synthesis. That's enough, and no need this enzymatic process. right? So enzymatic process, it is not required. So if you want to remember this, you can go with it. Okay. So, but it's no need that one, right? So just you make your preparation easy. Don't make your preparation complex here. So you selectively select the means compounds. Okay, like here the means as my idea here the S-ibuprofen is very easy, and norfraxin, right? Norfraxin, what is it? Naproxen. Naproxen is easy to remember, and this is also easy, I think. Okay, propranolol, it is easy to remember because very simple synthesis, right? These three things, and one more synthesis we'll see. Phenylalanine, it is difficult, I think, because the structure is very, it is large structure and complex structure. So you can skip this synthesis. Okay. And then we'll see. Yes, diltiazem is important actually. Ramipil also some difficult where the structure is some complex here, right? So, and here the diltiazem, this is means it seems some complex structure, but it is important actually, right? So it is important many times in the uh, previous exam. So we'll see the synthesis of diltiazem here. Yes. So it is a calcium ion channel blocker, right? So generally in the ion channel inhibitions, right? So ion channel inhibitions, we have variety of ion channels like calcium ion channels, potassium ion channels, chlorine ion channels here, sodium ion channels, right? So all these are the ion channels here. So ion channels, you know that these are the receptors actually. Ion channels acting as the receptors. They are having some kind of gated mechanism. Okay, so like just say here, right? So they are having this kind of arrangement here, right? So this ion channel here, and they acting as a gate, okay, to allow the, okay, this is the ion channel actually, right? And they are allowing the ions through the, okay, for example, calcium is there, okay, so calcium ions or the potassium ions or the sodium ions here, chloride ions, right? So they will allow these nutrients, okay, so they will allow the nutrients through okay, through this, and when the means required concentration of the calcium ions or the potassium ions are uh, entered through this one. Generally, we call this is the influx. Okay, influx of the calcium ion, right? So they will allow for the influx of the calcium ion here, right? So after the sufficient calcium ions are entered through that, then the gate will be closed here, right? And no further passing of the calcium ions will be takes place, right? Generally, this calcium ion is activating your smooth muscles, okay, and it operates or it controls the heartbeat generally, right? So it controls the heartbeat, means your heartbeat like the smooth muscles will be regulates your heartbeat here, okay. The influx of the blood, outflux of means inflow of the blood and outflow of the blood, so that thing will be controlled by your calcium ions, right? So for that, the required calcium will be entered through these ion channels here. And for that, these ion channels are using, means they are acting as a, what is that, gate here. Okay, just kind of gate, right? So sufficient calcium are entered, then it will be closed. The ion channels will be closed here. Okay. Then when that particular process, like, okay, what is that? We call that systole diastole. What is we call that? Expansion, yes. Or expansion and constriction of right, smooth muscles and expansion of smooth muscle, right? So that will be takes place here. Then again the outflux of calcium will be takes place. right? So it is a continuous process where the influx of calcium ion and outflux of calcium ion, right? So that is controlled by your calcium ion here. Okay, it regulates the right how much calcium ion concentration need to enter and how much calcium ion concentration other calcium ion need to go outside here, right? So that will be regulated, controlled by your ion channels here. Okay, calcium ion channels. For each and every ion channels, we have the different names. Like if they are regulating the calcium ions, then we call that is a calcium ion channels. If they are regulating the chlorine, we call the chloride ion channels. And if they are regulating the what is that influx and outflux of your sodium, then we call the sodium ion channels. Right. So in that here we have that topic, a separate topic is there. So we'll discuss in the further classes actually. Yes, fine. So when that process is done, when that contraction and expansion of your muscles or the heartbeat is takes place, again that outflex, that thing will be takes place here, right? And sometimes, right? So due to that due to some factors, right? So where the ion channel, calcium ion channel functioning, right? Means the calcium ion channel is failing its function. Okay, due to some factors. What are those factors generally? As I told in the first class, like hurry, worry, curry, isn't it? So these are some factors like hurriness due to your anxiety, your tensions. Okay, worriness, your depression, and curry means in the food habits here. Okay, so due to all these factors, so that particular ion channel is it is right. So it is failing its function here. So in that case, what happens here? The more influx of right, the more influx of calcium ion channels will be takes place, right? Then what happens here? If more calcium ions is entering inside here, then so they will over stimulate your heart muscles, right? If the concentration of your calcium ion is increasing or the becoming more, then the more activation of your smooth muscles takes place. Then what happens here? So the more blood flow will be takes place, isn't it? So if smooth muscles gets over activated, over stimulated, then the over expansion and over contraction, that means over blood circulation means inflow. What is that? Over the flowing of your blood will be takes place. Generally, we call that is a high BP. Okay, high blood pressure. So more development of your blood pressure, more blood pressure development will be takes place, right? We call that is a hypertension here, high BP. Okay, development of high BP, that is hypertension. Okay, so means that when it is happening here, when the calcium ion channel is failing its function, so more influx of calcium is takes place here. Okay, so in that case, so we'll use a diltiazem, 2S, 3S, diltiazem. This is the drug compound, antihypertensive drug. Diltiazem nothing but it is a antihypertensive drug. So it blocks the, okay, it is a calcium ion channel blocker, right? So this drug will be, okay, so it blocks the calcium ion channel and it regulates the influx of your calcium ion. Okay, so if it is blocking the calcium ion channel, then there is no probability for entering the calcium ion. So then the calcium ion concentration becomes normal here. Okay, so that is a mechanism involved in this particular diltiazem generally. Okay, fine. So in that case, we use a diltiazem drug as a calcium ion blocker, right? Calcium ion channel blocker here. Yes. So yes, the structure of this calcium ion channel is you can see means that is diltiazem is, you can see this is the right. So benzene. What is this? This is thio. Thio as what is this? seven member, is it? It is seven member, right? Eight member. 1, 2, 3, 4, 5, 6, 7. Yes. This seven member. Yes. So benzene is
thiazepine.
yes, thiazepine. Nice. Yes. This is thiazepine ring. Okay. Thiazepine ring with some substitution of the methoxyl, right? So methoxybenzene and some tertiary amine derivative. So this is the structure, you can remember this. And it is very important actually because I found, right? So I found where it is repeated. So many times it is repeated in the examination. Synthesis of guilty agent. Yes. So thiazepine ring means ring core moiety is attached with the N tertiary amine group and methoxyl benzene, right? Yes. Next, the synthesis is very simple. Simple because the structure is very large structure and some complex. It seems like a complex one, but synthesis will involve very simple reagents and simple steps are involved. You can see. Only thing is, yeah. So where the synthesis begins with dimethoxybenzene. Sorry, paramethoxybenzoaldehyde, right? Paramethoxybenzoaldehyde. So when it is treated with this particular ester compound, right? What is that? Yes. So what is it? Methyl chloroethanoate, isn't it? Yes. Methyl chloroethanoate, where it is undergoing some reaction. That epoxide, how it is epoxide taking place? Here is aldehyde. Yeah, fine. So there are one step is skipped actually here. So right, so here CHO, this is a carbonyl center, right? CHO here. And yes. Here is yeah, you can see this sodium methoxide, right? Base sodium methoxide is abstracting the proton from this particular carbon, and it generating the carbon ion here. Okay, and this carbon ion is right. This carbon ion is attacking at this electrophilic carbonyl center, right? Electrophilic carbonyl center. Then we are getting this right. So alcohol, right? We are getting this alcohol, and by NGP, right? So by NGP, where the expulsion of this chlorine is taking place, right? So by NGP, where the expulsion of your chlorine is taking place, and we are getting this epoxide derivative here, right? So actually here some expansion, two more steps are coming in between here. Okay, so they are condensed two steps actually. Here is the one step is the generation of the carbon ion. So right, so this methoxide ion, it is abstracting the proton and it is generating carbon ion. You will get the carbon ion here. Okay, and it is carbon ion is attacking at the electrophilic carbonyl center here. Then you will get the alcohol here. Okay, OH, this C double bond O, so it becomes OH here, right? And this OH here, one more base. You can take one more base, right? Here you write this, then you take one more base, that is methoxide ion again, and it is abstracting the proton here, and it you can get this O minus here, right? Oxide ion, and this oxide ion is by NGP, so it is removing your chlorine, and we are getting this oxide ion, right? So that is steps which is skipped here. Yes, fine. Then actually here resolution by lipase. So they are done the resolution means I think here they are getting the racemic mixture here. So some steps are skipped actually. Okay. So here we are getting the plus or minus epoxide derivative here. Right? So simply mention here plus or minus. That's all. right? So we are getting the two isomers, this racemic mixture, and by resolution by lippage, so we are right. So separating this particular trans derivative like 2 or 3s here. Then the opening of this particular epoxide ring with amino thiophenol. Okay, so orthoamino thiophenol, and orthoamino thiophenol is going to open your epoxide ring here. Then the cyclization, very simple. Okay, then further by cyclization, right? Because here this amide formation, right? By amide formation, where the cyclization is taking place here. Right? Very simple. Here the C double bond, this ester, right? So it is attacking here. Then methoxide is going out here, and we are getting this amide formation, right? The amide formation is taking place, and by attachment of your side chain, right? N substitution is taking place. N substitution with dimethyl ethyl chloride. Tertiary amine is okay. By taking that tertiary amine, where we are getting this N substitution by hydrolysis. Finally, we are getting this particular guilty agent. Very simple synthesis, actually, right? Right. So this is your guilty agent synthesis. Right. So I think right. So these 4 syntheses, okay, are easy to remember here, and remaining things are, I think, it is somewhat complex. Okay, yeah, this particular indinavir sulfate. Okay, indinavir sulfate, and one more is what is this? Ramipril, right? And one more is so we left 3 syntheses actually, right? I think what is done. We have to Ramipril and phenolapril, right? Ramipril, phenolapril, and indinavir sulfate. These 3 syntheses, we skipped these 3 syntheses, right? So if you are able to, okay, so remember this, you can go with this also. But I think whatever the synthesis we discuss now, so these are very simple synthesis. So better to go with this synthesis here, right? Yeah. Right. So yeah. So I'm going to stop. Right. So I'm stopping here. So we'll discuss the further means next topic in the next week here. Right. Okay, ma'am. Good evening to all.
Okay, sir. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.